Good afternoon, my name is Ian Coley. I'm the General Manager of Advanced Computing and Simulation at AWS, which means that high-performance computing and all simulation workloads belong to the incredibly talented people on my team. And today, I'm going to talk to you a little bit about how we think about high-performance computing workloads on AWS, how we perform them, and then with the help of some of my friends from Ferrari, they're going to give you a real-life example of some of the benefits that they've seen by moving some of their high-performance computing workloads onto AWS. So a little bit of summary of what we're going to go through is I'm going to give, just for a quick refresher of anyone that isn't familiar with where high-performance computing is active throughout our world. I'm going to give some examples of that. I'm also going to talk a little bit about how we specifically at AWS think about high-performance computing as opposed to maybe more traditional views. And then we're going to hear from, again, my friends at Ferrari. And then as a little teaser, at the end, I'm going to give you an example of an integrated machine learning / artificial intelligence, since that's the new buzzword we have to use, integration with a high-performance computing workload. I'd like to start out with an idea that really informs how we think about high-performance computing at AWS. And for me, it's kind of mind-blowing that it's been almost 20 years since William Gibson first said, the future is already here, it's just not evenly distributed. Well, the same could be said for supercomputing resources, which, as we're seeing, especially in this era of generative AI, are so key to bringing the future into the present. That many people globally, traditionally, have not had access to supercomputing-like resources. They have been held by some cognoscenti that have said, oh, you have to get a certain priority and a certain queue in order for your workloads to be deemed acceptable to run. But now, in the era of high-performance computing on the cloud, we really feel like we're starting to enter true democratization of supercomputing resources. And if you had the benefit of hearing Adam's keynote this morning, which I hope you did, if you didn't, go back and listen to the video, please. I think he said supercomputing at least 6 times, and the number of exaflops that currently performed on AWS another half dozen times. We have now given the ability of anyone with a credit card and an internet connection to have access to some of the most prized resources available to humanity. And then we let them innovate and think about how they can best use them. It truly is an exciting time to be involved in high-performance computing and see what new researchers, engineers, students can come up with to use these resources now that they have access to them. But again, what is high-performance computing when we talk about that, and how do people use those resources today, specifically in industry? Some of our most well-known areas of high-performance computing are computational fluid dynamics, figuring out the airflow over a vehicle to work both on the speed, the aerodynamic aspects of it, as well as the fuel consumption of it. We see seismic and reservoir simulation. So in our energy companies, looking to ensure that they are making the most efficient use of discovering and extracting resources that are so important to fuel this next season of innovation. Remember, it takes energy to run all of these CPUs and GPUs that are performing all of these workloads. We also see incredible advances in genomic sequencing, where customers like Eli Lilly are sampling billions of potential molecules and finding potentially life-saving molecules that can be applied to drug discovery through the power of high-performance computing. But what does HPC specifically in the cloud look like? We've talked a little bit about what HPC is, but what is special about it in the cloud? Well, according to analysts, I've given you lots of numbers up here about how it's growing. The overall HPC industry itself continues to grow, but we're starting to see a point where those who are making procurement decisions, whether they be large national laboratories in the United States, whether they be, again, energy companies, financial services companies, biomedical companies, they're starting to say, you know what? Maybe before I had a 1,000-core system in my on-premises data center, but you know what? As soon as those things run out, whether it be amortized over 3, 4, 5 years, pick your favorite model, I'm going to ensure that the next time it's much smaller and that I have some elasticity that I can use from cloud resources. And the reason we see that is because when you're talking about HPC resources, that flexibility is so dynamic. And that's a thing that we hear over and over and over when we talk to customers. And that's one of the keys of what we do when we think about HPC at AWS is just like the way we treat any problem. It's all working back from the customer. And we're hearing that over and over again is like, I need more elasticity. I need the resources that I want applied to the portion of my workflow exactly when I need them. And so we've developed, you see at the bottom there, a number of services, a number of instances based upon that feedback from customers. And this helps to continually inform our long-term strategy. So what is one of those things I hear consistently from customers is, I have to make an optimization decision when I commit to a large on-premises cluster. And I get a team together and we evaluate our various workflows and our jobs and we say, okay, I think that this architecture will solve about 70% really, really well. And then we'll fill in the rest. And so what you find is that you have to make sacrifices. None of that architecture is specifically created for that portion of the workflow. It's just kind of a best fit. And then you spend the rest of your time trying to keep those cores busy. So either you're got too much compute capacity available, and so then you're sitting there with cores that are just burning energy and not providing any actual business value or research value to anyone. Or you've got the opposite problem, where now you've got this extremely long queue where your innovation is stuck waiting in a queue, and all your resources are kept really busy. That's great for your, showing your CPU utilization. But how do you measure the cost of that innovation that's stuck in a queue? So again, when we talk to customers, what I hear is, I really want elasticity. Yes, there's a portion of my workflow that I may want to keep on premises. Maybe I want to move another data set and another workflow entirely into the cloud. But as I ease into this cloud migration journey, I want to take a portion of my fixed resources that were formerly in a data center, and I want to migrate that into AWS. And why? Because I want to have that flexibility. I want to say, you know what? For this portion of my workflow, it can really take advantage of acceleration. And so I can run a cluster of GPUs to accelerate that portion. And then when I'm done with that portion, I just shut it down. Whereas maybe that isn't sufficient demand for me to make that capital procurement decision and to buy that many hardware resources to put into my on-premises data center. But with the flexibility of the cloud, you can tailor that architecture, stand up exactly the architecture you need for that portion of your workflow, shut it down, go on to the next one, repeat, rinse, repeat over and over again. And so you get that flexibility of having exactly the architecture you need applied to your computing problem exactly when you need it, and no more, because when you're done with it, you shut it down. What's another thing I hear from customers when I talk to them? They say, you know what? I'm really thinking about this not just as HPC, but I'm thinking it as what some will call interactive heterogeneous supercomputing. Or another way of saying what we call simply HPC plus. So it's HPC plus machine learning, HPC plus artificial intelligence, HPC plus quantum, to where now that I've got my workflow in such a way that I can apply the specific computing resources that I need to that portion of the workflow that need them, I can think about, wow, okay, before this segment of my workflow was entirely based on CPUs, but what if now I'm able to move it to accelerators? Again, not moving my entire workflow, but just this portion to it. Or at some point when quantum computing should have become a reliable option, as we heard about in the keynote last night from Peter DeSantis, we're making progress there with the logical qubit that we've created. But when it can actually do a portion of my workflow more efficiently than standard computing, because I've modularized my workflow now, I can apply quantum resources to that. Again, not to the whole thing, because it doesn't make sense to have that entire workflow applied to a quantum computer, but for that portion that can take advantage of it, then I can apply quantum to it. Everything else, I can apply CPUs, GPUs, or whatever the next thing is, FPGAs. Pick your favorite new technology because of that flexibility that you've created in this workflow. So to summarize, we've heard, I want flexibility in time, and I want flexibility in architecture. And so this has informed our long-term product vision into what something I like to call Project Any. And again, this is our North Star that I want you to think about, and that we're not there yet, but this guides our product roadmap and how we think about our long-term strategy. Because ideally, what I would like to be able to do is have any customer, again, be that a high school student in sub-Saharan Africa, be that a research scientist in the Middle East, or be that an engineer working in the fields of India. I want them to be able to run their workload. So any person, any workload, anytime, anywhere. Again, any person, any workload, anytime, anywhere. That's my dream. That's our North Star that we're shooting for. Again, we're not there yet. We've got a lot of work to do, but that's how we think about where we're headed and where we see the innovation in high-performance computing coming from. Because we can't predict where that next discovery is going to come from or how somebody's going to use these resources, but what we can control is how we give them access to them, how we make that easier. And so now that we've talked about kind of where we're headed, let me come back to where we are today. So when we look at high-performance computing on AWS, honestly, it looks a lot like high-performance computing, period, because there's not a lot different about high-performance computing. Newsflash, whether you do it in a data center, in your on-premises environment, or you do it on AWS Cloud. You need access to compute. You need access to performance storage. You need a highly proficient network, especially for your low latency dependent jobs. You need to have occasionally remote visualization. That's one area that we'll talk a little bit about later that is super important for the cloud and an additional resource, but it's also been used in on-premises. And you need to have some sort of an orchestrator, so something to set up, tear down the cluster, something to schedule resources. So let's start out with compute. One of the things that we've done over the last couple of years is we've said, you know what? The era of users having to say, I don't know, is a C instance or an R instance or an M instance the best of my workload? Well, they're all kind of similar, but with different memory. But I'm not really sure if that's key for HPC. And we kind of did a best case optimization and made customers fit their workloads into things that weren't really created solely for HPC. Many customers were super happy with it. In fact, the C5N is still one of our most popular HPC instances for customers. But we said, what if we actually tailor-made some instances specific for high-performance computing workloads? And the main thing we wanted to convey there is these workloads are so important that they're worthy of having a specific instance family around them that isn't just one instance or two instances, but is a whole family of our own Graviton-based, as you see there with the HPC 7G, AMD-based with the HPC 7A, and Intel-based with the HPC 6ID. So the goal there being, depending upon which one works best for your workload, maybe you need an extremely fat node that has a lot of memory bandwidth and a lot of on-instance storage, so you go with the HPC 6ID. Or maybe you don't. Maybe you need something that has, a little more memory bandwidth, but not quite as much, a little bit thinner. Maybe you're doing some weather simulations, so you go with the HPC 7A. Or maybe like many of our customers, you're saying, you know what? It's not just price for performance I'm looking at right now, but in order to improve the impact that my computing is having on the environment, I really care about my performance per watt. And so I want to balance out how much I'm saving versus how much energy I'm using. And that's where we see customers choosing the HPC 7G. One of the things that's key to enabling us to create these whole family of instances, or actually the whole explosion of EC2 instances you've seen over the last several years, has been this innovation of the AWS Nitro system. And what's so incredibly powerful about this Nitro system is not only does it allow us to iterate quicker and to give you more instance options, but it increases your security because we offload all of those previous areas of a normal like Zen hypervisor that would take away CPU and memory, but would also like make you think maybe your instance has some vulnerabilities that maybe somebody could get to it. You can't with the Nitro system. We simply can't get to your computing resources. They are solely allocated to you. And one of the things I want to point out there is when you first glance at that bar chart, you may go a little bit, wow, it looks like the difference between virtualization and metal, there's some pretty big gaps there. And then I want you to look at what the actual numbers say. Like I could have cheated or made it look really good with this, really high bar from 0 to 100 and shown how close, almost really close. But we're high performance computing people. We want to be very exact. I want to point out the actual differences. And when we see on these codes, there are some differences. But we're talking about 99 to 99.7% of the actual hardware performance that you would get from a bare metal instance that you're getting from a virtualized instance. So we've practically eliminated any sort of virtualization penalty. And here are the number of EC2 instances in the middle that we've seen customers really take advantage of. It's not just the HPC family. While again, those are geared directly for HPC workloads. We have customers that are performing their high-performance computing workloads on any of the number of these instances in the middle here. So I went over the computing. Let's talk about networking. One of our innovations that we created over the last 5 years is our elastic fabric adapter. And I'm really excited that it's getting a lot more press now that there's such an interest in AI and ML, because it has been a key component of the innovation that we've had in high-performance computing workloads on AWS. I mean, when I started, we didn't have EFA. We only had like 20 meg connections. Now we've got super high throughput connections. We're talking 3,200 gigabits per second. We talked about this morning with the Trainium. Also, our latencies, we didn't have EFA, so our latencies were maybe 30, 40 microseconds. Now with the elastic fabric adapter, we're pushing down into the single-digit microsecond latencies. So how do we do that? And what does that even mean? How did we create a new protocol to do this? Elastic fabric adapter is based upon our own protocol called the Scalable Reliable Datagram. And what's cool about SRD, as we call it, is that it's based on ECMP, equal cost multipath. And what that does is say, you know what, when I get to a branch, I'm going to say that it's the same cost if I can get to either multi-directional to get from one point to another. Just take either path, who cares? They're even. Whereas other protocols, such as InfiniBand, really they kind of analyze all the possible point-to-point connections, and then they just hammer data across it. And then if you have any sort of issues, a problem with that, then it's got to recalculate, retransmit, things like that. we said we need a protocol that takes advantage of the scale of AWS's internal networking. What happens if we just spray packets across it? And what's cool about SRD is it can accept those out-of-order packets. And then if it needs to, if the application actually requires it, it reassembles them in order on the other end. So we're taking advantage of the scale of AWS's network to provide performance that traditionally you would only see in extremely low latency environments. And what you see in that graph there is that we're almost reaching ideal scaling there. And what that means is basically for every node that you add, you continue to accelerate. Because with many codes and with many networks, you reach a tipping point to where the inter-process communication, the node-to-node communication, just starts to bog down the calculation. And so it doesn't advantage you in any sense to add additional nodes to the calculation. But we can see at least up to 400 nodes in this calculation, we got almost perfect scaling with the Elastic Fabric adapter. I'd be happy to answer that question afterwards.
Okay,
thanks. Next, we talked about compute network. Now storage. Amazon FSx for Lustre. For anyone that's been doing high-performance computing for a while, Lustre is kind of the gold standard for extremely performant POSIX-compliant file system. It's an open source project that's been around for decades, came out of Lawrence Livermore National Laboratories, and can give millions of IOPS very consistently. And so what we did is we looked out and we said, okay, if this is the gold standard for storage, then how do we then give that to our customers in a way that is a managed service, such as what they expect from the majority of AWS services? So we've created this Amazon FSx for Lustre that dynamically creates file systems just like you can dynamically allocate compute clusters. So in this way, again, this is not like, think about it, your data center where you buy a petabyte of storage, it's up all the time. Here you have a portion of your workflow that requires some data. Maybe you keep it in S3 so it gets aged out as it just ages over time down to cheaper layers. Then when you need an actual POSIX-compliant file system in front of it to work with, then you pull it up, it populates the data, it's there with your file system, then you do your work, you complete that portion of your workload, you shut it down. Similar to the computing, you're only paying for the storage that you use for that Lustre file system, and then you're aging off any of your other data to S3. And then one of the things we heard from customers is, that's really cool, but I've got a bunch of data in my on-premises data center, and I still want access to it because I want to compute against that on AWS. So can you build me some sort of a cache? And so we created Amazon File Cache, which takes that Lustre client and puts it as a front end to either on-premises file system, or you can even use it as a fast cache for any other NFS v3 version file system on AWS, or even put it just in front of S3. And so with these two offerings, FSx for Lustre and Amazon File Cache, we feel like we've got a pretty performant file offering there for customers to perform their high-performance computing workloads. Next up, the orchestrator. So when customers are looking to schedule these resources, how do they think about that? Well, AWS Batch is our cloud-native scheduler. So when customers are looking to run a job queue, a compute environment, that's all that AWS Batch requires is, I've got a queue that I want to put a bunch of jobs into, and then you define what kind of computing you need to accomplish those. Now the key is containerization. So AWS Batch supports ECS on EC2, ECS Fargate, or EKS. So depending upon whatever your favorite containerization is, AWS Batch can spin up resources dynamically in those environments for you, allocate them, run the jobs, scaling up and down, and then shut it down. And then finally, AWS Parallel Cluster. Now, AWS Parallel Cluster is our open source cloud orchestrator. It's based on the popular CFN cluster open source project. And we took that on as AWS and said, we need to more productize it to ensure that customers know that this isn't just some open source project that's out there, but you have the full support of AWS support behind it. And so we created AWS Parallel Cluster to show that. And this helps orchestrate your scheduler, your storage, your networking, and your compute. And now our new toy that we created, that we announced at Supercomputing just a couple weeks ago, I'll fly through this pretty quickly, Research and Engineering Studio on AWS. And so what Research and Engineering Studio is customers came to us and they said, what, this is going to sound strange, but I really miss those old Portal days. For those of you that are familiar with NICE, there was this product, NICE engine frame, that is still out there and supported. It's just really old technology, and some customers love it and swear by it, even though it doesn't quite look like it's built with soap, but pretty close. And they said, can you give me a more modern version? I want a portal that I can access my resources with a single pane of glass. So we created something that allows customers with Research and Engineering Studio, or RES, to, depending upon their persona, I'm an admin. I want to create and allocate resources and virtual desktops for employees to access high-performance computing workloads. Or on the other hand, I'm a research scientist. All I want to do is come in and fire up things. I don't want to have to think about it. And so you can see a number of the features here. We said, okay, we want to have access to resources. We want to have something that's project-based. I want to have something also that I don't want to have a separate permission system to where I have to go in and think about IAM roles and how they map to Active Directory. And we're assuming that you've got your on-premises or on AWS Active Directory set up, and you're just going to import from it. So we really need to be able to do that. And by doing that, we simplified access to these cloud-based resources by giving customers a number of ways to interact with these remote visualization consoles that they can then share with one another. They can copy them, they can share them, they can allocate them. An administrator can then say, you know what, I want to allow you to not share your desktop, or I want you to only restrict it to where you can only share it with this other subset of users, maybe within your same group. And so what we see is customers taking advantage of this integration with Active Directory and with the remote visualization to be able to conduct these workflows that previously, let's just say, would be a little arduous to set up. Here you can see you can assign permissions, roles, and it's all within a single pane of glass. You're able to control that and dynamically allocate it to users at your discretion as the administrator. And again, it's very project-based, so you can then, one of the things that's kind of hard to see, unfortunately, on the font here, but see that little bar there is I'm tracking the cost. So I'm saying, okay, I'm predicting that this is the amount of cost that you're allocated to that project that you should spend, and it looks like you may overrun that. And that's up to me as the administrator if I want to allow them to continue to schedule resources and to use beyond that, or if I want to put a hard limit on that and they just need to figure out how to make it fit within the constraints of what they have. So it's that cost modeling and budgeting that we really see customers appreciating about this tool. And then again, flexibly accessing a number of services. So you could set up a virtual desktop that's connected to a really small instance. You could set a virtual desktop that's set up to connect to a very large graphical instance. It's all up to you and the administrator's control. And here's what I talked about, being able to control whether you share it with one person or a work group. If you have any questions about Research and Engineering Studio, I invite you to go to aws.amazon.com/hpc/res and try it out. It's all open source. You can play with it today. And let us know what you think. And now I'd like to invite up Stefano Maltomini from Ferrari.
Thank you, Ian. So my name is Stefano Maltamini. I'm working in Ferrari in the racing department. I'm the head of digital and data over there. And today, together with my colleague Marco Gaudino, we are going to present you how Ferrari is using the HPC and the cloud for the design and development of Ferrari road cars. So let's start with the issues we were facing with our HPC on premises and the opportunities were found in the cloud. So first of all, we had reached a saturation of the computing capacity, and we had no more free space in our data center. So clearly here, going to the cloud offers the opportunity to access a wide availability of computing power without the need of a physical space and without the need of continually refreshing the physical assets. Second point, we had the need to cover temporary computing peaks. So as also Ian was saying here, HPC in the cloud has a great advantage. It is the ability to tailor HPC solutions very close to the business needs. And this is moreover important when the business needs are changing over time. Third point, we had the need also to enable experimentation and to run continuously innovative simulations. So today, for example, more and more computational fluid dynamics codes are GPU optimized. We were interested in accessing this computing technology, and more in general, the latest computing technology, without the need of upfront investment and the need of long procurement cycles. This slide represents the on-premises architecture. So very simplified, you see on the left the data center based in Maranello, Italy, and a representation of the on-premises resources. On the right side, upper, you see the a list representation of the services provided by the digital and data team. Among these services, you see HPC support. So it's the digital and data team that in Ferrari is supporting the users in accessing HPC computing power. And it's inside this team that the experimentation and the implementation of HPC in the cloud has performed. Internal users are mainly engineers coming from the research and development teams that are using HPC for design and development of the road cars. More in detail, we are talking about computer-aided engineering workloads, affinity element method simulations, and computational fluid dynamics simulations. So this on-premises architecture has evolved into a hybrid architecture. So you see here a representation that is very close to the AWS reference model. So we have basically connected our on-premises environment to the AWS Cloud through a direct connect. And users on our side are now able to access parallel cluster service, engaging the exact number of computing instances and defining the computing power they want to use to run their jobs. We are also taking advantage of Amazon Aurora as database management system, FSx as a performance file system, NS3 as an object storage system. All these systems, all these services are within a virtual private cloud. And we made this choice for our security requirements, and this choice fully met these requirements. So that's all regarding the hybrid architecture. Now we'll leave the stage very fastly to Marco, to my colleague Marco, who is going to present you the results of the performance we have achieved with this hybrid architecture in comparison with the on-premises architecture for some HPC workloads. Thank you.
Thanks, Stefano. Hi, everyone. I'm glad to be here with all of you. My name is Marco Gaudino, and I'm working in Ferrari Racing as a digital and data application architect. So, as Stefano already said, today I'll share with you some results and insight of our tests and experiments that we made after we deployed all the services we described previously in the cloud. So let's start by understanding what we made. Basically, we started by comparing the performances of our Ferrari on-premise clusters versus the cloud one in a so-called baseline setup. Here we used EC2 instances with the same number of computing cores as the on-premises machine. So having a look to the table, here you can easily understand that we made our comparison at a different level of computational time and data to be uploaded to cloud. So, in particular, looking at the figures into the table, you can understand that they explain how long it took to run a simulation in cloud versus the on-premise. Please keep in mind here that when we are talking about the computational time for the on-premise, we are only considering the simulation time. When we are talking about computational time for the cloud, here we are considering the simulation time and the time needed to upload the data to the cloud. So when the number is blue, it means that the on-premise performed better than the cloud solution. And it mainly happened when we had a lot of data to be uploaded to the cloud or when we had a computational time short. When the number is green, it means that the cloud performed better. And as you can see here we observed a performance increase of around 20% compared to the cloud, compared to the on-premise, sorry. However, after we made this first test, we thought to implement some improvements to our cloud setup and to repeat again the test to have some more benchmarks. So the first improvement that we made regarded the network part. And basically here, we enhanced the network data transfer speed by 4 times. As you can see from the table here, the cloud performed better right from the start. And also here, at the end, we observed a performance increase of 20%. Another improvement that we made on top of the previous one was the one that regarded the user experience. And in particular, here, there was the introduction of the DCB, as Stefano already mentioned during the hybrid architecture description. This scenario was really important for us because this was the first time that we compared a full cloud scenario with an on-premise one. But what does it mean? It means that we didn't just do the computational work in cloud, but also the pre-processing of the data and the post-processing of the data. But what does it mean in practice? It means that we uploaded the same amount of data in cloud, but our users were able to download 80% less data compared to the previous scenario. Why? Because they did the post-processing of the data in cloud, so they downloaded only the result they strictly needed. And we here had a pretty good result. In fact, as you can understand from the green numbers, the cloud performed almost better in all cases. And also here, we observed a performance increase of around 20% compared to the on-premise solution. Now, let's move on to the last improvement that we made to our cloud setup, in addition to the previous one. And here, we had the possibility to use the full cloud potential, and in particular, its scalability characteristic. Here, we have doubled the number of the computing cores of our EC2 machines compared to the number of the computing cores of the on-premise ones. And as easy to understand from all the green numbers in the table, here the cloud outperformed the on-premise setup, reaching a maximum of 60% higher performance than the on-premise setup. So 3 times better the previous scenario. So now, having covered what we have achieved by implementing an HPC in cloud, let's go deeper to our next step. First of all, we would like to enhance the user experience of our users by improving the DCV solution based on the business needs. So going to reduce the utilization of the on-premise setup for the pre-processing and the post-processing of the data. Furthermore, we would like to optimize the cost efficiency ratio of our hybrid architecture. What I mean? Essentially, we would like to introduce some cost analysis tool by AWS to have a better control of our cloud spending. Moreover, we are looking forward to use maybe a different purchasing model like the reservation one instead of the pay-as-you-go model. And as Stefan already mentioned during the introduction, we would like also to introduce EC2 with GPUs because there are some cases that can have a beneficial aspect from this technological enhancement. So at the end, for sure, we would like to extend our HPC use in cloud when we will achieve the points above. Thank you for listening, and with that, I'll leave the stage again to Ian.
Now, one thing I didn't hear anybody heckle from the audience was, well, that's not fair. You doubled the cores that you had on-prem. Well, that's the beauty of the cloud. Exactly, like you can't just lift and shift an entirely new data center, or well, you could. In some cases, if you have enough raised floor tile, you could put an exact duplicate once your procurement goes through in 12 to 18 months that duplicates your on-premises resources. But here you see they were experimenting, and they said, you know what? Wonder what would happen if we doubled the resources. And now he said, well, now maybe we need to do some fine tuning, and we put cost into the equation, so we're looking at price for performance, not just sheer performance. But that's what the power of the elasticity of HPC on AWS gives you, is that you can make those experiments. You can try things and see how your workloads perform, and then iterate. So now I promised you at the beginning that I was going to go into an example of machine learning integrated with high-performance computing. We see lots of promising studies out there. If you look especially in the references and the small lettering there around physics-informed neural networks, or PINs. It's an interesting area to research if you look. And how do we think about where this advent of this HPC plus, of taking a portion of my workload and seeing how it can be either accelerated or modified by integrating it with generative AI or machine learning. And how does that impact how we think about even the design of our workflows? So this case that we created was we took a generative AI called Stable Diffusion. So anyone hear of Stable Diffusion? No controversy at all, artists, royalties, things like that. But hey, isn't it fun to just invent, I don't know, an astronaut riding on a pony, and just have it spit out something? It's pretty amazing what it can do. But we said, what if we use that for car modeling? Why not? We said, let's try to tell Stable Diffusion to make us a aerodynamic sedan. We don't like the look of our current sedan, so give us an aerodynamic sedan. But all Stable Diffusion can do is throw out a bunch of two-dimensional images. Right? And it's not smart enough to really take into account what the actual aerodynamics of that image are. But what can we do with that 2D image so that we can actually try to figure out what the aerodynamic characteristics of that image are? So we can use this tool called a NERF to take that 2D image and actually do a 3D point model. And once we have that 3D point model, then we can feed that into OpenFOAM, and we can run our mesh and see how does that image actually perform when we're calculating drag coefficients against it. And now what's cool about this is, again, because we're got a workflow that's in the cloud, is we can just iterate and iterate and iterate. And so in this case, we've used a package called TwinFlow that is our digital twin orchestrator that is powered by AWS Batch that we talked about earlier, our cloud native scheduler, to just run simulation after simulation after simulation, taking, here's a snapshot, turn it, running this whole pipeline. Here's a 2D snapshot, turn it into 3D. Now run the actual OpenFOAM code, see how it performs. And here's an example of what it kind of looks like. So we've got this 2D picture of the sedan. Now we turn it into this 3D point cloud. Now we actually run our CFD workload against it. We see how fuel efficient it is. And here you can see the various ideas that we came up with when we're iterating through that with the real drag coefficient of them. And so this is kind of a toy model. Again, we're just playing with concepts and ideas to see how might one take, in this case, just a generative AI prompt to say, okay, make me a more fuel efficient sedan and turn it into an actual workflow. So in a generative AI model that knows nothing about the actual CFD workload. We're just using that as a prompt, but we've got this pipeline now to perform that workload. And you can see not all these are good because Stable Diffusion doesn't know about the impact of putting that little spoiler on the back or not. It doesn't know about the impact of the headlights on the front. But it's something that can allow our artists and renderers and car designers to maybe think up new concepts that they hadn't considered originally, just by allowing the AI to stimulate a little bit of that imagination. And that's where we really see this HPC plus AI coming into effect, is not taking away work, but actually accelerating work by giving us more areas that we can innovate, giving us more ideas to work from, and in some cases, drastically cut down the subset of problems that we're looking at. In some cases, we could potentially have a subset of design models that could be almost infinite. But here it gives us, our designer, an area to think, okay, what if I just focus on headlights in this version? And so that's where we find it really interesting as just a precursor of what might come in the future. Now, I can't finish this talk without bragging on my team a little bit, because we were just at Supercomputing 2 weeks ago awarded Best HPC Cloud Platform, now for the 6th year in a row, and just totally coincidentally, that's the entirety of my time here at AWS, running the HPC team. And I want to point out, because the text is a little small, this one on the left, so if you'll forgive me for a moment, I'm actually going to do one of the things they never tell you to do, and I'm going to pull out my phone, and I'm going to read you the text of this award on the left, just because this is where it's really impactful to me. This is what keeps me so excited about high-performance computing, is the real research and real-world impacts that we're having. And so this was the Editor's Award for Best Use of HPC in the Cloud, and it says, the Dana-Farber Cancer Institute developed a computational platform for drug discovery, completing its largest high-performance computing run using 5.7 million Intel-based virtual CPUs running on AWS using the Virtual Flow platform to identify and create a library of 70 billion molecules that might be used to treat cancer and other diseases. This publicly available library speeds research safely and effectively by identifying candidates in days versus months. Days. Think about this corpus now that has been created that other researchers and scientists can go and evaluate for potentially life-saving treatments solely because of the scale of the cloud. This is the reality of the elasticity of the cloud, and this is what gets me so excited about high-performance computing on AWS. So whether you're doing drug discovery, designing a new car, doing financial services modeling, end-of-day risk calculations, whatever your workload, we can handle it on high-performance computing on AWS. So I invite you to think about how can you best take advantage of these resources. Thank you for your time. I would say if you were intrigued by any of this, if you have further questions or want to find out even more, here are a number of sessions about high-performance computing that are still going on the session. One of those has already occurred, but you can pull it up later and watch the recording from my colleague Srinivas Tadipalli. He'll go even into more detail on some of those ML plus HPC workloads. And then I would ask, please fill out the survey. It's important to us. It gives us feedback. It helps us know how we can improve and do better next time. So thank you so much for your time. And if you do have any questions, I will answer your question about using Elastic Fabric Adapter. I invite you to please come up to the side afterwards. We'd be happy to answer them. Thank you so much.